We're glad to have Professor Kinney again. He'll be giving his second lecture on inflation. Over to you, Will.
Okay, thanks. Let's get right down to business. We have a lot of good stuff to go through. So we left off last time talking about the sort of the basic structure of inflationary models, which are based on some kind of a scalar field potential. The idea being that a scalar field that is displaced from its true vacuum, either in this case, so this is a symmetry breaking potential, or we'll be looking at cases where there's no symmetry breaking, where this is just shaped like a big bowl. Actually, those are the simpler ones to do calculations in. And when the field is up here in its unstable equilibrium, you have a potential energy associated with it. And since this field permeates all of space, you have a potential energy. This potential energy acts like a cosmological constant, right? And then this cosmological constant then drives a period of inflation, after which some period of inflation, this field drops off the maximum. When it drops down to its minimum again, inflation ceases, and couplings between the scalar field and the other particles of the standard model, or whatever extension to the standard model you want to be working with, then the field energy decays into all of these other particles, creates a hot thermal equilibrium universe, and creates the initial conditions for the Big Bang. So in this sense, there are sort of two senses of what people mean by the word Big Bang that tend to get conflated with each other. One of them is this hot thermal equilibrium boundary condition for the expanding universe. And in a very real sense, inflation takes place before this time, and inflation is a zero temperature Bose-Einstein condensate that then later decays and heats up the universe in the reheating process and brings the universe to thermal equilibrium. That happens at the end of inflation. On the other hand, in a standard Big Bang cosmology, that the hot radiation dominated early universe is cut off by the initial singularity, right? Which is it's a boundary in time. So the initial singularity is an infinite, in spatial extent, 3 surface that cuts off that 3+1 space-time at a finite time in the past. That initial singularity now is, so the second sense of the word Big Bang is the initial singularity. And that initial singularity is at the very least pushed into the past by inflation. And it's still an open question, and one that I haven't answered in these lectures so far, as to whether or not that initial singularity can be removed entirely from the space-time, or whether it's still present at some pre-inflationary point, okay? And I'll have a couple of comments on initial conditions for inflation a little later today, but I'm gonna very much try to avoid talking too much about initial conditions until probably the 4th lecture. So let's make this quantitative. We can write down a stress energy for a scalar field by foliating the space-time along fluid flow lines. So we're going to take our time-like direction to be along the direction of the world lines of the fluid elements. And we're going to take our space-like hypersurfaces to be orthogonal to those flow lines. So then we introduced before these notions of projection operators. So a time-like projection operator along the fluid 4 velocity, and a space-like projection operator along the orthogonal to that fluid 4 velocity. And then we can identify in this foliation, we can identify a pressure, which is just the Lagrangian, and an energy density, which is the Hamiltonian for the scalar field, right? 1/2 phi dot squared plus V of phi is the total energy, 1/2 phi dot squared minus V of phi is the pressure. And it's straightforward to show that if you then work in a coordinate basis, in co-moving coordinates where the fluid flow is everywhere exactly along the time-like direction, you can show that the stress energy tensor takes the form of a perfect fluid, okay? And then in this basis, what we have, if we write down stress energy conservation, what we have is an equation of motion, which is a standard classical equation of motion for a scalar field, with the exception that it has an additional term, which is a drag term from expansion. The field, like anything else in an expanding cosmology, tends to lose momentum. And that drag term is then given by the Hamiltonian of the field. Now, one thing I want to point out here is that this is a deceptively simple equation because it's a nonlinear equation. right? So despite the fact that it's sort of uncomplicated in form, it actually contains some unexpected depths, right? Because of its nonlinearity. In order to have inflation happen, and I remember there was a question yesterday about, well, do you have to have slow roll to have inflation? One answer to that question is yes, in the sense that the field has to be rolling slowly enough that you are dominated by the potential rather than by the kinetic term, right? So as soon as the kinetic term becomes small relative to the potential, you have an equation of state that approximates a cosmological constant that P is approximately equal to minus rho. And then that is a necessary condition for inflation, that the field velocity has to be small enough that this pressure is less than or equal to at least minus 1/3 rho, okay? So that is a hard condition on whether or not you're inflating at all. Then there's the slow roll approximation, which is a little more subtle than that because of the fact that this is the approximation that you're ignoring both the field velocity in the field velocity in the Hamiltonian, or the field kinetic term, but also this phi double dot in the equation of motion for the field. And this results in the standard slow roll attractor solution, which is that the expansion rate is just given by the potential, and the field velocity is just given by the derivative of the potential. And this is a very useful limit, first of all, because it is an attractor solution. And second of all, because it allows pretty simple analytic evaluation of all of these inflationary quantities that we're interested in, right? So it allows for analytic solutions. There were a lot of questions yesterday regarding initial conditions for this. How does the field end up in this unstable equilibrium? How do you get to this slow roll inflationary solution, and so on? One answer to that is that this is an attractor, right? So as long as you have a homogeneous scalar field configuration that somehow ends up pretty close to this unstable equilibrium, whatever initial conditions, whatever boundary conditions you start with, you will always flow toward this slow roll attractor solution. And tomorrow, when we talk about non-slow roll solutions, we'll really dive into this question of dynamical transients versus attractor behavior and inflation. But the important point with respect to initial conditions here, and I was thinking of an old movie called Cannonball Run, which is like a 1980s Burt Reynolds movie that, since most of you guys probably mostly watch Bollywood, you probably aren't familiar with. But there's a scene in the movie where two race car drivers sit down in this car, and one of them looks up and says to the other, "The first rule of Italian driving," and he reaches up and snaps off the rear view mirror of the car and throws it out the window, "is what is behind me is of no importance." Well, inflation is like Italian driving, right? Once you get, as long as you somehow get a large enough and homogeneous enough bubble of false vacuum, that bubble begins to expand exponentially, and it completely obliterates all traces of whatever the initial conditions were. You no longer care where that inflationary solution came from. As long as it goes on for long enough, it will basically, you will always end up in this attractor solution. And the details of the initial conditions are completely unimportant for any observables, because all we see is what happens at the very end of this inflationary phase. So for the remainder of this lecture, I'm going to push aside the question of initial conditions. We will return to them in lecture 4 and just talk about the properties of this attractor solution. Tomorrow, we will talk about non-attractor solutions. And then in the 4th lecture, we'll start talking about larger questions such as embedding and string theory and boundary conditions and so on. So we're going to take these equations of motion, and we're going to look at this particular attractor solution and look at its properties. And in particular, today we're going to study perturbations primarily. So here is the first exercise for the students. So here is your basic equation of motion that we derive basically from the classical field equations for the scalar field. You have this nonlinear equation of motion with a drag term that is where the drag on the field is proportional to the expansion rate, and the expansion rate is proportional to the Hamiltonian. Notice here, I'm not making any approximation yet. I have not made a slow roll approximation. This is the exact system of equations. So the exercise for the student is to take this second order differential equation and show that it can be busted up into two first order differential equations on the condition that the field itself is monotonic in time. That is, that we can always write the field velocity as a function of the field itself, right? So as long as the field is monotonic, we can write the Hubble parameter as a function of the field. We can write the kinetic term also as a function of the field. And then what we can do is we can take this second order equation of motion and we can break it up into a system of two first order equations of motion. This is called the Hamilton-Jacobi formulation. And it's analogous to a Hamiltonian formulation in classical mechanics, where you take a second order equation of motion and break it up into a system of first order differential equations, okay? And so this is well known in the literature, and it's straightforward to derive this relationship between these two things as long as the field is monotonic. And this monotonicity is really important, and we'll come back to it, especially when we talk about ultra slow roll inflation. But basically, the outline of the proof is you take this thing, take its time derivative, plug that time derivative back into this equation, and then you can come up with this the system of equations. So if you haven't been through this exercise before, I'll leave that to students to do. We're going to use this Hamilton-Jacobi formulation, which is entirely equivalent to the original equations of motion as long as the field evolution is monotonic. So let us now define what we mean by slow roll in a formal way, right? So I gave an informal statement of the slow roll approximation. This is a formal statement of the slow roll approximation as follows. I define what I call the slow roll parameter epsilon is this is an exact equation where epsilon is the first derivative of the Hubble parameter with respect to the field in the Hamilton-Jacobi sense, divided by the Hubble parameter squared. And as long as you're in slow roll, as long as the kinetic term can be neglected in the Hubble parameter, then this can be just written as a function of the potential, that it's just this familiar expression for the first slow roll parameter, that it's v prime over v squared. The slow roll parameter is significant for inflation because we can write the equation of state for the scalar field in terms of epsilon. In particular, that the relationship between the pressure and the energy density, it depends only on this parameter epsilon. And as long as epsilon is much, much less than 1, you have that P is approximately minus rho, and you have an inflationary expansion, okay? So now I'm going to restate the slow roll approximation as the approximation that this equation of state parameter is less than 1. As long as it's less than 1, you are in an inflationary phase. If it's greater than 1, you are in a decelerating expansion. And that's because the equation of state is just given by this parameter epsilon. So now I can write my Hamilton-Jacobi equations in this limit as I can neglect this epsilon term in the Hamilton-Jacobi equation for H. And notice that gives me just exactly the expression that I had before, that by neglecting the kinetic term in the equation for the expansion rate, right? So that gives me exactly what I had before. And similarly, I can find that the field velocity is given in terms of h prime of phi. So these equations are exact. These are slow roll approximations. And so in the slow roll limit, as long as epsilon is small, then I can write phi dot is equal to v prime over 3h. I end up with the same result that I got before. So this is simply a more rigorous way to derive the slow roll approximation in terms of directly in terms of the equation state for the scalar field, and dividing it up into inflationary and non-inflationary spacetimes. So this allows us to come up with a schematic diagram of how a model for slow roll inflation works, how the background dynamics for any particular scalar field potential works in inflation. And it's very straightforward. So as long as the potential is flat enough and the field is rolling slowly enough, right? So if I have, for example, some long plateau, or there are a variety of ways you can accomplish this, but as long as this slow roll parameter is less than 1, which is identically equivalent to saying that the second derivative of the scale factor with time is positive, that is because you can rewrite the Ray-Choudhury equation exactly as, right? So this equation for a double dot, you can rewrite this equation, which in normal form is, you've seen it a lot like this. In the Hamilton-Jacobi formalism, you can rewrite that exactly as it's just h squared times 1 minus epsilon. So a double dot is positive when epsilon is less than 1. A double dot is negative when epsilon is greater than 1. So when epsilon is less than 1, you are in an accelerating phase, and the expansion is accelerating. This is your inflationary phase. When epsilon is greater than 1, that tells you that the expansion is decelerating, and you have exited the inflationary phase. And the boundary between these two is the point at which the potential gets steep enough that you no longer can neglect the kinetic term, where the drag from cosmological expansion is no longer dominating the equation of motion. And at that point, you enter an oscillatory phase at the bottom of the potential, and then coupling to the other degrees of freedom in your problem reheats the universe, inflation ends, and you enter a radiation dominated phase, and Bob's your uncle, you have a big bang, right? So this is the basic outline of background dynamics in inflation, and just about any inflationary potential you want to talk about is going to work this way. There are, alternative models where you can do this with a field with instability in an auxiliary field and stuff, but basic single field inflation works according to these principles. Okay. Whoops. Okay, so let's clear all drawings. And how do I get rid of the software updater? This is unfortunate. I'm going to have to, hang on. Let me just, I need to stop my screen share for a second. There we go. All right, I will restart my screen share. Apologies for that. Start from current slide. And reshare my screen. There we go. Okay, good. Oh, now I started from the first slide. Let's go down. Okay, where were we? Back up. Okay, good. No, back. There. Stay. All right. So that's the basic outline, right? So let's look at an example of this. Let's look at how we work this out in a very simple case, right? So how we find this boundary between inflationary and non-inflationary expansion. And let me see. Let me turn the annotate back on again. Draw boxes. Good. Okay. Now, so let's take a look at probably the simplest kind of potential, which is the chaotic inflation potential, which is just a simple bowl at m squared phi squared. So all you have, your field potential just looks like 1/2 m squared phi squared. Simplest scalar field theory you can possibly imagine. So in order to figure, and the way that inflation works in these models is, instead of being up near an unstable equilibrium, the field is just displaced way, way, way up this potential. And if it's far enough up the potential dominates over the kinetic term, right? So as long as the potential is big enough, you can create a large enough drag term in the potential to drive inflationary expansion. And we can see this as follows. So given a potential that looks like 1/2 m squared phi squared, we can calculate epsilon using the slow roll approximation now. So we're going to assume slow roll from the beginning. We're going to derive the inflationary and non-inflationary regimes. You can check the consistency of this after you have the solution by going back and plugging it back into your equation of motion and verifying that the assumption, that the approximation we're assuming of slow roll is actually a good one. And what you will find, and this is a consequence of the attractor behavior of slow roll, is that in fact this ansatz of slow roll at the beginning is self-consistent. That you really are in a slow roll phase in these regions. So all we do is take v prime over v squared. So we work this out. And it turns out that the parameter epsilon, this equation of state parameter that governs the inflationary behavior, is just given by the Planck mass squared divided by phi squared. By the way, I am using the reduced Planck mass throughout in these lectures, right? So this is the regular Planck mass divided by the square root of 8 pi. So epsilon is 2 m Planck squared over phi squared. And so inflation ends then when this parameter passes through unity. Notice that epsilon is small when phi is big, and epsilon grows as phi drops down toward the origin. So as the field rolls down this bowl, and when it's high enough up, when it's far enough displaced from its minimum, this equation of state parameter is less than 1, and you have inflationary expansion. As it drops toward the minimum, eventually it drops through a critical point, and that critical point is given by an ending field value that we call phi sub e, that ends up being around the square root of 2m Planck. So one lesson we learned from this is that you have to have transplanckian field excursions in order for this, in order for inflation to happen. The field has to be displaced from its minimum by larger than the Planck scale in order to have inflationary expansion. This is a trick that you can do for you can write down your favorite single field potential. You can just plug V prime over V into this, and you can figure out what regions, for which regions are epsilon less than 1, for which regions are epsilon greater than 1, and you have the basic inflationary background dynamics worked out. It's that simple. All right. Any questions about this before we start in on perturbations? Yes. I'll take the question, but I don't think I can. I think I need some help from the tech people. There we go.
Unmute. Yes, just Shantraj, can you allow me to unmute, please? Shantraj Gopi, I am not able to unmute them. Shantraj Gopi.
Oh, I saw the question in the chat box, actually. The question is, why is this called chaotic inflation? Okay. That name was given to it by Linde, who wrote the first papers on this in the 1980s. And the word chaotic comes from the fact that the initial conditions are assumed to be just like some random thing. And what you do is you have some sort of random field fluctuations, and in certain regions that field will have fluctuated high enough up the potential to set off inflation, at which point you forget about the boundary conditions, as I suggested, and it goes. So it's basically a reference to the initial conditions, which, remember, we're not allowed to talk about today. We don't care. So in the potential diagram, why is there a rise in V of phi after reheating, right? Well, this is just basically a symmetry breaking potential. So the reason the potential goes up is that this is your minimum. This is your true vacuum. So this is exactly the same thing as we plotted before in the, let me get my slide selector up. So this is just basically looking exactly at a potential of this type, at this sort of hilltop potential where you have a true vacuum that's down here at the minimum of the potential. So it's a schematic of something that looks a lot like the potential for a Higgs boson or something with a little broader plateau up on top. It's just a schematic, nothing more. One more question. I don't think I saw the end of that.
When phi tends to infinity, the phi goes to 0 in this example. Can you tell me what this means physically?
I'm sorry, I don't. When phi goes to infinity, phi goes to. I don't understand the question.
Epsilon tends to 0. That's what it is.
Epsilon tends to 0 when phi goes to infinity. That's right. That's the farther up the field you go, the farther up the potential you go, the more this approximates a vacuum equation of state. In the slow roll approximation, remember, we've already assumed slow roll here, right? In fact, what happens is once the field goes up high enough, the energy density of the field becomes Transplanckian, at which point you lose control of the calculation, right? So then you have to understand quantum gravity once the thing gets high enough up. The interesting thing is that even when the field value has a Transplanckian excursion from the minimum, the energy density of the field need not be Transplanckian, and so that you can still ignore quantum gravity and do the calculation self-consistently. What matters is not whether the field is Transplanckian, and what matters is whether the energy density is Transplanckian. Okay. Okay. Shall we continue? Do you remember we're good to go? Okay.
Yes, please go ahead.
Okay. So today's lecture, we're going to talk about perturbations, right? And a lot of this is standard lore in inflationary cosmology, right? So those of you who are familiar with inflation will see the formulas we'll derive today will be familiar. But I want to dive into a little bit of the general relativity here. And in particular, what I'm going to do is I'm going to derive the standard formula for the curvature perturbation twice. I want to do it one way in sort of a heuristic way using what's called the delta n formalism that allows it, that's a very nice intuitive way to do the calculation. And then I want to go back and look at it again from a more formal standpoint of gauge invariant Mukhanov variables and see the structure of this and understand exactly why these expressions actually work, because the standard expression for curvature perturbations is a little strange, and we'll talk about why it's strange in a minute, right? So I'm going to derive a familiar formula for those of you who are familiar, at least familiar with inflation. For those of you who aren't, if this is the first time you're seeing it, if you're having trouble keeping up, especially, don't worry, you'll be able to, one of my philosophies here is you'll be able to go back and look at the video and the slides and actually work through some of this stuff. And nothing I'm going to talk about today, everything I talk about today is well covered in the literature. This is very bog standard stuff, but it is complicated. And what I want to do is approach it in a way that illuminates some of the structure of it. So the basic idea of perturbations and inflation is as follows. So far we've been talking entirely about classical evolution. So we have the scalar field potential that has a plateau up here that is flat, that supports a long period of inflation, which is what we need in order to solve the horizon and flatness problems. And today we'll make that quantitative, how much inflation we actually need. And then down here you have some sort of minimum where it oscillates about the minimum. It has a true vacuum, and oscillating about the minimum, it reheats and so on. So we've talked about the classical behavior in the first part of these lectures. But of course, there is the Heisenberg uncertainty principle. So superimposed on that classical evolution, there are going to be quantum fluctuations in the field. There are 0-point fluctuations in the field. And that means in the case of the scalar field that's driving inflation, this field is going to, in terms of the equation of motion, this adds a stochastic term to it, right? So these quantum fluctuations are going to bounce this field up and down the potential a little bit in addition to its classical motion. You also have virtual particles in the vacuum, right? So we know that in any quantum field theory in vacuum, the vacuum is not empty, it's full of virtual degrees of freedom. And these virtual particles are actually physical things, right? You can measure it with a Casimir effect with Hawking radiation from black holes, at least in principle. You can measure the presence of vacuum fluctuations in quantum birefringence, which is something that's really cutting edge experimental science right now. But in inflation, the point is that if I have some little quantum fluctuation that is at very short wavelength, very high energy. So if I look close enough at my space-time, what I'm going to see is these little virtual particle pairs coming in and out of existence. That because of the inflationary expansion, because of this exponential expansion, if I take a quantum fluctuation that starts out at short wavelength, almost instantly, because the expansion is so rapid, that short wavelength fluctuation is going to be redshifted until its wavelength is longer than the horizon size of the universe, right? Another way to think of this is in terms of virtual particle pairs. If I have a virtual particle pair that pops out of the vacuum, normally what would happen is that they would recombine in a very short period of time. And so these particle-antiparticle pairs are coming out of the vacuum and then recombining. In Hawking radiation, for example, you're probably familiar with this cartoon picture of how Hawking radiation for a black hole works, which is that you have this virtual particle pair pops out very near the horizon of the black hole. One of them falls in, and one of them is carried, and one of them goes off to infinity, right? This is a cartoon analogy for Hawking radiation. The real physics is in vacuum definitions and so on, and we'll actually talk about that later. But this process of stretching these quantum modes out to superhorizon sizes in inflation is a lot like Hawking radiation, except in an inflationary spacetime, the virtual particle pair pops out of the vacuum. And instead of recombining, the expansion is so rapid that it sweeps these two particles so far apart that they're outside of each other's cosmological horizons and they can't recombine anymore because they're causally disconnected. This is an analogy to Hawking radiation. So the difference here is that instead of this being a black hole horizon, which is a trap surface, this is a cosmological, it's a de Sitter horizon, which is an anti-trap surface. Everything is swept out of it. And this sweeping of virtual particles outside of the horizon is a process that's a lot like Hawking radiation for a black hole. And it's the process by which perturbations in inflation are generated. And today we're going to go through the quantum field theory of how this works. So what we're going to do is semi-classical quantum field theory in a time-dependent general relativistic background, okay? So, but the basic picture is I take a short wavelength perturbation, it is rapidly stretched out to long wavelengths, and once that wavelength is larger than the horizon size, that quantum mode becomes classical, gets frozen into the background, and is imprinted as a classical perturbation in the space-time evolution. And what we're doing today is a calculation of the amplitude and the spectrum of these perturbations. So let's take a look at this qualitatively. And here's the basic picture, is that during inflation, the horizon size is approximately constant. It's growing very slowly because when epsilon is not exactly equal to -1, that tells you that the Hubble length is growing rather slowly with time. So on the vertical here, we have this line is the horizon size as a function of the amount of expansion. Okay. And then at the end of inflation, you transition to a radiation-dominated phase, and the horizon starts to grow relatively rapidly as after this point where epsilon passes through 1. So over here, you're inflating. Over here, you're in the radiation-dominated phase. And then what happens to a particular quantum wavelength, so if we plot a quantum mode, that mode is going to redshift proportional to the amount of expansion. During the inflationary phase, the horizon size is approximately constant, so that mode redshifts. It starts out smaller than the horizon size, redshifts until it's larger than, until it crosses outside the horizon, spends a whole lot of time larger than the horizon size, and then eventually during that later radiation or matter-dominated phase in the present universe, this mode re-enters the horizon as a classical perturbation, and once it's inside the horizon, it can source galaxy structure and so on, and cosmic microwave background perturbations and the like. Now, this geometry means something. There's one important qualitative consequence of this, which is the following, is that long wavelength perturbations exit earlier in inflation, and short wavelength perturbations exit later in inflation. And we will see later on, and those of you who are familiar with inflation probably know this already, is that the amplitude of the perturbation, the power of spectrum of the perturbation, is proportional to the Hubble length at the time the perturbation exited the horizon, usually. And so because the Hubble length is approximately constant, that tells you automatically, just qualitatively, you know that this perturbation spectrum from inflation is going to be something very close to scale invariant, but not quite, because the Hubble parameter is actually decreasing with time, right? The horizon size is getting a little bit larger with time, which means that the Hubble parameter, the expansion rate, is decreasing a little bit with time. So what you should find is you should have a little bit more power on large scales and a little bit less power on small scales. This is called a red spectrum, okay? And this is in fact exactly what we see in perturbations in the universe. So we already know in particular that this basic setup for inflation, because long wavelength perturbations exit early and short wavelength perturbations exit late, that you should have an approximately, but not exactly scale invariant spectrum. And that spectrum should be such that you have slightly more larger perturbations on long wavelengths and slightly smaller perturbations on short wavelengths. This just comes out of the geometry of the problem and the null energy condition. Basically, the fact that the horizon size of the universe has to be either constant or shrinking tells you that from inflation, you generally expect to see a red spectrum of perturbations. And that's, of course, exactly what we see in the universe. So hooray, right? So we don't even have to do any math, and we can work out one simple prediction of basic single field inflation models, which is that you should see a nearly scale invariant, but slightly red spectrum of perturbations in the universe. This is completely consistent with what we see in the CMB, all right? So now let's get quantitative. The first thing we want to know is, how much inflation do we have to have? In particular, we have to have enough inflation so that a wavelength that is currently entering the horizon, so if we say that this right here where I'm marking on this box, suppose this is us today, where this is the longest wavelength perturbation that we see in the cosmic microwave background, so the CMB quadrupole or something like that, is just entering the horizon now. You have to have had enough expansion during inflation, so this mode exited the horizon at some point during that inflationary phase, very, very early on, okay? So the condition for the quantitative condition for solving the horizon problem is that a mode of order the horizon size, a scale of order the horizon size today, had to have been of order the horizon size during inflation early enough, and the inflationary phase has to go on for long enough that that mode was actually inside the horizon during the inflationary phase. That's the boundary condition that we have enough inflation in the universe. So let's work this out quantitatively. So suppose we have the current co-moving horizon size is just A naught H naught. And let's take some mode with co-moving wave number K, right? So this is co-moving wavelength is basically you're taking a wave that is expanding in wavelength with the expansion rate of the universe. You factor the expansion rate out so that basically is a wave number in the universe today, right? So this is just a number. It doesn't change with time. It's a label that labels our particular mode. So this is the horizon size in co-moving units, units that are expanding with the universe. This is the wave number in the same co-moving units. And so when that mode, if that mode is re-entering the horizon today, that tells you that that is just, so essentially K divided, co-moving wave number K divided by the current horizon size is given by the value at horizon exit during inflation, right? So this is K over A naught H naught today is equal to 1 if the mode is just entering the horizon today. K is equal to AH is the point at its value at horizon exit. And we are saying that is also equal to 1 by definition, right? Because we're saying it exits the horizon. So the wave number in units of the co-moving horizon size today is just equal to the horizon size at which the mode exited the horizon during inflation divided by the horizon size in the current universe. We can expand that out a little bit more, so we can bust that up into two different epochs. One of which, let me go here. We can look at the period before it exited the horizon, and then look at the period after it exited the horizon. So before it exited, or the period after it exited the horizon, but inflation is still happening, and the period after inflation ends. So before the end of inflation and after the end of inflation, I'm sorry. So before the end of inflation, it is being stretched outside of the horizon, which is this term. After the end of inflation, the universe is radiation dominated up until matter radiation equilibrium. And I'm making an approximation here that reheating is instantaneous, that when inflation ends, I immediately enter a radiation dominated phase. If reheating proceeds for a little while, there's going to be some other terms in here, but for simplicity, I'm ignoring them. And then another factor that just depends on the evolution of the co-moving horizon size from matter radiation equality to the current universe, which is just a constant, right? It just depends on our parameters for our LCDM cosmology. So we can plug all this stuff in. It's kind of it's a little bit of a dirty calculation. In particular, we're going to write that the scale factor is exponential in some number of e-folds. And I will define this in just a minute. Essentially what I'm doing is I'm just going to write the scale factor as an exponential of this number n. N is called the number of e-folds. And notice in particular this weird sign convention where it's actually negative n, and I'll talk about that in a minute. So that means that the log of the scale factor, the logarithm of this ratio of scale factors from when the mode exited to when to the end of inflation now, is just equal to the number of e-folds at which, so we're taking the end of inflation to be n is equal to 0 and the number of e-folds to increase as we go backward in time. So that's equal to the ratio of scale factors then is equal to the number of e-folds before the end of inflation at which the mode exited, and the difference in the Hubble parameter from when the mode exited to the end of inflation. And we're going to also make the simplifying approximation that the Hubble parameter is close enough to constant during inflation that this term is, the logarithm of that ratio is approximately 0. Okay, you can include that if you want, and if you want to do high precision calculations, you have to. But for our purposes here, it's not necessary. We can approximate the Hubble parameter as being approximately constant. So this is the evolution of the mode. This term that happens before the end of inflation is just given by the number of e-folds before the end of inflation at which the mode exited the horizon. Now, the subsequent stuff that happens after the end of inflation, we're assuming that we have a radiation dominated phase. You can relax this assumption, and there are lots of papers written about this, is just equal to, this is if we take a radiation dominated phase immediately after the end of inflation, lasting all the way up to matter radiation inequality, then during this radiation dominated phase, AH goes as just the inverse of the scale factor. So we can simplify this expression as just a ratio of scale factors between matter radiation equality and the end of inflation, which then, assuming thermal equilibrium, we can rewrite as temperatures. So we can rewrite this log of scale factors as the log of temperatures, where T sub r is the reheat temperature after inflation. That's the temperature at which the hot Big Bang, at the boundary condition at the Big Bang, at which inflation ends and the radiation dominated phase proceeds, and the temperature at matter radiation equality, which we know from LCDM cosmology, plus a small correction factor that depends on the difference between the number of relativistic degrees of freedom, right? Because if this temperature is high, you're going to have whatever extension to the standard model you're going to have more degrees of freedom in relativistic species, which then introduces this correction figure, which is a standard thermodynamic figure in early universe cosmology. And I'm not going to dwell on it too much. This thing is, this entire logarithm is a small number of order 1. It's not a large correction to the basic equations. And finally, the third term in that expression, which is the ratio of horizon sizes between matter radiation inequality and today, you can calculate in an LCDM cosmology, and this is a nice exercise for students as well in basic thermodynamics of cosmology. It turns out that ratio is about 3.8. All right. So we have all the terms that we need in order to calculate the number of e-folds of inflation that are necessary in order to solve the horizon problem. In order for a mode of order the horizon size today to exit the horizon during the inflationary period and then and freeze out at super horizon scales. In particular, we know that for a given wave number k, the number of e-folds k at which it exited the horizon is given by this ratio of the wave number divided by the current horizon size. We can rewrite this in terms of the reheat temperature in terms of a fixed temperature, this is about 10 to the 15 GeV, about the grand unified scale. A correction factor for the number of relativistic degrees of freedom between the gut scale and the matter radiation equality, plus this constant that is all the other stuff that went into this calculation, which is a factor of about 60. So now if we want to talk about a mode that is of order the horizon size today, well, that means that this logarithm just vanishes. We can get rid of it, right? So in particular, we can, so let me see, I can just draw an arrow and say that thing just ends up being equal to 0 when k is equal to a naught h naught, when the mode is of order that is equal to the horizon size today. So that tells you that for reheat temperatures around the gut scale, that you end up with a number that's somewhere around 60 e-folds of inflation is when that mode that was of order the horizon size today exited the horizon. So this is this, and once again, those of you who are familiar with inflation already will recognize that number 60. You need about 60 e-folds of inflation at least in order to solve the horizon problem. And that's just the geometry of this problem with perturbations. Now notice that inflation, you can have inflation, let me get back to my box. Inflation can go on for an arbitrarily long time before that. You can have more than 60 e-folds of inflation and there's no problem there. You could have 10,000 e-folds of inflation. You could have 1,000,000 e-folds inflation, because the only thing that matters in our horizon size today, so modes that are our horizon size or shorter are all in this region of the plot, which means they all exited the horizon in this region. They exited the horizon during the, so modes of order the horizon size today are smaller, all exited the horizon in this last 60 e-folds of inflation. So everything that we have observational access to are in this little box at the end. Everything over here is still super horizon size in our universe, and we have and are in principle unobservable. Okay, so we can only see that last tiny little 60 e-folds of inflation. Presumably inflation goes on for much longer. Once again, this is just a consequence of the geometry of the problem. It's the simple that these are the only things that are currently inside our horizon today. Everything that exited the horizon size earlier than that is still outside of our horizon today, and we can't observe it. Okay. So now let's write this down in terms of a scalar field theory. So now we have, this is essentially, we need at least about 60 e-folds of inflation, and this depends on the reheat temperature in particular. So if the reheat temperature is lower than 10 to the 15 GeV, this logarithm is negative, and we need fewer e-folds of inflation to solve the horizon problem. So if inflation happens at around the gut scale, we need about 60 e-folds of inflation. If inflation happens at less than the gut scale, we need less inflation. Okay, so let's do this in terms of a scalar field now. How much inflation do we need? So we define the zero of the number of e-folds to be the end of inflation. And we write the scale factor goes as e to the minus n. So that means that the number of e-folds is actually increasing as we go that way. As we go earlier in inflation, the number of e-folds that gets bigger. This is the sign convention that we're using. It's sort of a weird sign convention that's very widespread in inflation. And since, and we know that, and this is just the Friedman equation then, that this number of e-folds is just minus the integral of the Hubble parameter with time. This is just basically writing down the definition of the Hubble parameter, that h is equal to a dot over a. This is just another way of writing h is equal to a dot over a. It's an identity. So now we can calculate if we have a particular scalar field that is inflating, right? We can use the slow roll approximation to calculate the number of e-folds as a function of the field value. So I label phi sub n as the field value n e-folds before the end of inflation. I can write that as this integral of the Hubble parameter with time, which then I can convert into an integral in terms of the field just by changing variables from t to the field value. This is once again assuming that the field evolution is monotonic. And then I can write this in the Hamilton-Jacobi formulation. As long as the field evolution is monotonic, I can write phi dot as a function of phi. I can use the Hamilton-Jacobi equation to write phi dot is equal to minus 2m Planck squared h prime, right? That's the second Hamilton-Jacobi equation. So now I have what I have here is an integral that it was this integral h dt. I have converted by assuming monotonic field evolution into an integral in terms of the scalar field. And if I write this in the slow roll approximation, h and h prime depend only on the potential, right? Or even better, an exact expression is I notice that this integrand in here is just 1 over the square root of epsilon. So now what I've done is rewritten this time integral as an integral over the equation of state during the inflationary phase. And so then I have that the number of e-folds of inflation is just given by the integral of 1 over the square root of the slow roll parameter epsilon, starting at the field value phi sub n and integrating forward in time until the end of inflation, right? Now notice that this phi n is calculable. We can just calculate using this from the slow roll approximation. We know that this has to be around 60 or so. So that allows me to calculate what that field value is 60 e-folds before the end of inflation, where perturbations of order the horizon size today exited the horizon. Let me show you how this works in practice, right? So a worked example of how to do this is as follows. Let's take our chaotic inflation example again. Well, remember that I calculated phi n before was that epsilon is just m Planck over phi squared. So I have that phi n is the square root of 2m Planck. So that means I know what this limit of the integral is. So that tells me that the number of e-folds in terms as a function of the field value of phi is just this integral of 1 over the square root of epsilon, which is in the slow roll approximation, is just the scale, it's just phi, right? Epsilon is 1 over phi squared, so 1 over epsilon goes like phi. And this is a simple integral to do. I get that this is just phi squared over m Planck squared. And then I can solve this thing for the field value as a function of the number of e-folds, which is just m Planck times the square root of 4n plus 2. Okay? So the point here is that I can use the slow roll approximation, calculate where the end of inflation is. I can integrate backwards and then calculate what the field value is a certain number of e-folds before the end of inflation. And that is calculating the point at which that the number of the field value n e-folds before the end of inflation, where a perturbation of a certain wavelength exited the horizon. And I can relate that to the wavelength in the current universe by so if I know the number of e-folds, then I can go back and I can use this, let me see, this expression. So if I know the number of e-folds and I know, for example, for a given potential what the reheat temperature is, then I can calculate what the wavelength of that mode is in the current universe, and I can relate this to observation. So this is how this formula is how I take the parameters from my scalar field theory and translate those into wave numbers in the current universe today. I do it in terms of the number of e-folds. So any questions about this process before we continue? This would be a good time for a slightly quick questions on this if there's any confusion, because we're going to start to go into the theory of metric perturbations. All right, guys. Nice. So everybody totally understands it, I'm sure. Okay. So let's talk about metric perturbations. This is something that we're very fortunate that you have some very good lectures by by David Wands, who is really one of the world experts in this stuff, right? So I am going to skip a lot of the details that he is going to be covering for me, right? And I want to talk about actually implementing this in an inflationary context. So a lot of the stuff that David is introducing in his parallel set of lectures, I am going to be now taking and applying to doing calculations in inflation in particular. And it's very fortunate that David is actually using the scalar vector tensor decomposition, which is the same formalism that I'm going to be using here. There's a whole alternate formalism based on the ADM formulation of the metric that is also widely used and is extremely powerful. The problem with the ADM formulation, in my opinion, although it's really a calculationally powerful thing, it allows you to do higher order expansions and Feynman diagrams involving graviton loops and a lot of very sophisticated things that you need to do, for example, for non-Gaussianity calculations and the like. But it's very algebraic. It doesn't have a lot of the geometric intuitiveness that the SVT decomposition does. And so this is a much more sort of physically understandable and intuitive way of looking at the problem. And I think it brings certain things to the fore that are swept under the rug normally when people talk about this. And I'll dive into a bit more detail about exactly what I mean by that as we go along. So now we're going to look at perturbations in the metric. All right. And so what we're really interested in is calculating density perturbations in the universe. These are the things that source the fluctuations in the cosmic microwave background. They're what source the structure and the cosmic structure and so on. This is basically the calculation you need to do in order to calculate any of the observables that are relevant for cosmology. So this is what you need to do in order to connect this abstract scalar field theory to actual data in the universe, to turn basically what's a bunch of theory into actually hard-nosed science that you can compare to data. And so what we're going to do is we're going to take the metric, which we have so far in the homogeneous case been assuming is just the Minkowski metric multiplied by an overall time-dependent conformal factor. And we're going to introduce linear perturbations to that metric, where those linear perturbations are delta G mu nu. And we can then, and I am going to take in the SVT decomposition, I'm going to consider only scalar perturbations. We'll talk about tensor perturbations later on, right? So as David has already told you, I believe, that this can be decomposed into things that transform as scalars, things that transform as vectors, and things that transform as tensors. In inflation, vector modes are exponentially damped and we don't care about them, so we forget the vector modes. The tensor modes are gravitational wave modes, and those are actually the simplest thing, and I'll talk about those in a minute. The complicated thing is the scalar modes. And so analogous to what David, the decomposition that David was doing, I think I'm using slightly different variables, but it's the same decomposition. I can take the metric and divide it and write it down as the most general possible combination of scalars that I can use to construct a rank 2 tensor metric perturbation. And this is the most general decomposition. And then I really don't have to worry about these 0, 0, and 0i components, basically because I can gauge them away. In particular, the 0i, the lapse function, I can set to 0 by a gauge choice, right? I have a lot of gauge freedom here, so I'm just going to gauge away the lapse function. And I'm sorry, the shift function, and I'm going to keep the lapse function and the spatial perturbations. The second thing is, so the two things I'm ignoring is, one is I'm going to gauge away the shift function, which is the 0i component. And I'm going to be interested in the asymptotic behavior of this, right? This behavior at very, very long wavelengths. And so this double spatial derivative on this transverse component is going to be proportional to my wave number squared in Fourier space. That's going to go to 0 at long wavelengths, so I can ignore that piece as well, okay? So I have two metric perturbations that I care about, is the lapse function, which is the 0, 0 component, and the curvature perturbation, which is this ij component in my spatial metric perturbation. And this guy right here is the thing I really care about. This is the thing I want to calculate because that is the metric perturbation that sources CMB fluctuations and so on. That's my curvature perturbation. And my goal here is to come up with a quantum calculation of the value of that thing in an inflationary background. That is our goal today. All right. First thing we do is we want to write down in this, remember in this fluid flow formalism of Ellis and Bruni. I think I said it was Hawking and Ellis last time, and I'd like to correct that. The paper I was thinking of, and I already put that up on the Slack channel as the paper by Ellis and Bruni, is that the four divergence of the fluid four velocity in the unperturbed space-time is just 3 times the Hubble parameter. And now we can calculate that in the perturbed space-time, and we find that that is equal to its background value plus a set of linear perturbations that depend on this lapse function A and the curvature perturbation zeta in the way that's shown here. Okay, so I can calculate essentially this is the Hubble parameter, the analog of the Hubble parameter in an inhomogeneous space that is linearly perturbed from a homogeneous background. And it's first order in those perturbations, we can calculate the divergence of the four velocity in that. So in the unperturbed universe, the change in the number of e-folds is just equal to the Hubble parameter times dt, or is equal to, in units of conformal time, is equal to minus AH times d tau. And we write down an analog in the inhomogeneous space, that now where my time variable is the proper time along the fluid world lines, and the analog of my Hubble parameter is just this fluid four divergence. And I find that this generalized number of e-folds in the inhomogeneous space is just given by this perturbed quantity. Notice in particular that since I'm integrating over the conformal time tau, the curvature perturbation ends up being a boundary term, and it drops out of the integral, and the effective number of e-folds only depends on the lapse function. Okay, because of the fact that you already have a derivative of the curvature perturbation with conformal time, and you're integrating over that, so you can get rid of it as a boundary term. All right, so my unperturbed space, in the flat space that I'm perturbing around, I have the usual expressions for the number of e-folds of inflation and the Hubble parameter, which is uniform, right? It's only time dependent. This generalized version of the Hubble parameter, this fluid four divergence in the inhomogeneous space, is actually a function of both space and time, right? So this is a function of x and t. This is a function of t only. And the generalized number of e-folds depends on the fluid four divergence and the lapse function in this way. So now we're off to the races, right? Let's talk about quantum field. And so now the idea here is that we are going to use quantum field theory to calculate this curvature perturbation. And we're going to show that, in fact, we can express the curvature perturbation in terms of the difference between this background number of e-folds and the actual number of e-folds on the inhomogeneous perturbed hypersurface. All right. So the endpoint of this calculation is that we're going to calculate this curvature perturbation in terms of the difference between this thing and this thing, where that difference is generated by semi-classical zero-point modes in quantum field theory. So let's look at how this works. How does the quantum field theory work in this time-dependent background, right? So in fact, we talked about before, we have this classical background evolution of the field, which is going to be the slow roll solution. And then we have a quantum background, which is these quantum perturbations, these zero-point modes where the field fluctuates. And I'm going to take the quantum perturbation amplitude to be just the field fluctuation, right? So whatever the amplitude of that field fluctuation due to the Heisenberg uncertainty principle, as it's bouncing up and down the potential, is going to be my, we're going to calculate this later, but for now, we're just going to say whatever it is, all right? So here's how this calculation works. Remember that we have these quantum modes where the field quantum fluctuations relative to this classical, right? So my flat background space-time is my classical slow roll solution. So I'm going to use that to define what I mean by that homogeneous background space-time that I'm perturbing around. And then these quantum fluctuations have the property that the field is either going to bump quantum fluctuations are going to bump the field up the potential or down the potential. These are not free field fluctuations in general, and certainly not in the field that's responsible for inflation. If there's a background field, if I just have some scalar field in this time-dependent background, these field fluctuations are going to be free field fluctuations. But the inflaton is special because when the inflaton gets bumped up the potential, that increases the energy density in the universe a little bit, because it's when it goes up the potential, it increases the Hubble parameter. So it increases the energy density, it increases the expansion rate a little bit. And similarly, when it bumps down the potential, it decreases the Hubble parameter and decreases the expansion rate a little bit. Notice, remember that we're comparing the number of e-folds of inflation on the unperturbed, on the classical hypersurfaces, with the number of e-fold of inflation on the perturbed hypersurface. And so if I'm changing the expansion rate with these field perturbations, that means that the field perturbations are going to couple into the number of e-folds at linear order. Another way to say that is these quantum fluctuations couple to gravity at linear order in perturbation theory, when the field that is fluctuating is in fact the field that's responsible for inflation, because when the field fluctuates, it goes up and down the potential, and that potential is what's setting the expansion rate for the universe. So the physics here is that field fluctuations couple to the curvature at linear order because they couple to the expansion rate at linear order, and it's the expansion rate that determines the curvature. And here's how this works, is that we can foliate our space-time in two ways. The first is we can look at the flat unperturbed space-time. So this is the space-time in which we're calculating this background Hubble parameter, h, right? So this homogeneous background Hubble parameter is defined on a set of hypersurfaces such that the number of e-folds is a constant. Scalar field fluctuations are going to perturb us up to a different hypersurface. And now we can take a second foliation of that space-time. We can redefine time and space to be hypersurfaces in which the field is constant, but the Hubble parameter is varying with time and space. That is, so if I take, these are called co-moving hypersurfaces. So if I look on co-moving hypersurfaces, I can calculate this generalized number of e-folds on these co-moving hypersurfaces is the integral of this fluid flow divergence along the fluid flow lines, along the proper time along the fluid flow lines. So I have two hypersurfaces and two definitions of the number of e-folds. On this hypersurface, the number of e-folds is a constant, but the field will be fluctuating due to quantum fluctuations. On this surface, I foliate it such that the field fluctuations are zero, but that means that the number of e-folds is going to fluctuate. And the curvature perturbation then, this zeta, because remember this was a surface term in the integral for the number of e-folds on co-moving hypersurfaces, then zeta is just given by the difference in the number of e-folds between the flat hypersurface and the co-moving hypersurface. And then I can write this in terms of the field as the derivative of the number of e-folds with respect to the field times the size of the field fluctuations. So this is called the delta n formalism, and it's a beautifully elegant calculation in that I can take, so let me go back here, right? Let me go back to my earlier slide, that if I do the fluid flow divergence like this, when I integrate that, right, I get this term inside the integral, and then I get a surface term. That surface term is now on the outside of this thing, and now using that surface term, I can calculate the surface term by taking the difference between this integral and the unperturbed background. And then I can rewrite that in terms of field fluctuations by just taking the derivative of this number of e-folds with respect to the field fluctuations times field fluctuations, and that gives me the co-moving curvature perturbation. So notice what I'm doing here, and this is important because people frequently refer to the co-moving curvature perturbation as a gauge invariant variable. This is not so. It is not a gauge invariant variable, it is a gauge fixed variable. Zeta is the curvature perturbation measured on co-moving hypersurfaces. In a sense, this is gauge invariant. So when people use the words gauge invariant, what they really do is they mean two things. One usage of the term is invariant under infinitesimal coordinate transformations. Zeta is not gauge invariant in that sense, because in fact it is the curvature perturbation on these surfaces of constant n is zero, right? So this is only defined on these co-moving hypersurfaces. Zeta is defined on a particular foliation of the space-time. So the second meaning of gauge invariant, which is more frequently used, is that what they really mean is gauge fixed, right? So if I define co-moving gauge, then I have this observable and co-moving gauge that I can calculate. And so zeta being defined to be the perturbation on co-moving hypersurfaces and gauge invariant in the sense that it doesn't make any sense on any other hypersurface, right? But it really isn't independent of how we foliate the space-time. If we foliate on flat hypersurfaces, zeta is by definition 0, and that's a perfectly good choice of gauge. So I can choose a gauge where theta is constant and zeta is non-zero, or I can choose a gauge where the curvature perturbation is 0 and the field fluctuates, right? And it's the difference between those two gauges, which it turns out in these calculations is perturbative, that allows us to calculate the curvature perturbation. Super important conceptual point that we're going to return to later. So now, if we know the size of the quantum fluctuation in the field on flat hypersurfaces, we can promote those quantum fluctuations up to co-moving hypersurfaces and calculate the corresponding curvature perturbation. So here's the way the delta n formalism works informally. And then I'm going to go back and do this in terms of actually gauge invariant variables a second time in a minute. Now on the flat hypersurfaces, I can treat delta phi as a free field fluctuation and ignore any general relativistic couplings entirely. I can calculate that amplitude, and then I can calculate the corresponding curvature perturbation by just promoting that field fluctuation up to co-moving hypersurfaces and calculate zeta. This is the idea. So let's look at free field perturbations in a de Sitter background, or an approximately de Sitter background. Now, so I know how to calculate zeta if I know delta phi on flat hypersurfaces. That's the delta n formalism. The next thing we have to do is calculate delta phi on flat hypersurfaces. We have to calculate the amplitude of these quantum fluctuations. This is semi-classical gravity. What we're doing is we're calculating the amplitude of quantum fluctuations in a time-dependent general relativistic background. Straightforward calculation. Those of you who have done inflation before have probably seen this. I'm going to take my field and I'm going to break it up into a background piece, which is only time dependent. That's a solution to the classical equations of motion. And then a field fluctuation, which is going to be quantum. All right. For these quantum modes now, I have to take into account, I can't get rid of these k-squared terms at the start, right? So I can't assume that the field is homogeneous, so I'm going to have to keep gradient terms. So it's straightforward to show that if these I'm going to take primes to be defined to be derivatives with respect to conformal time. And it's straightforward to show that the equation of motion for these field fluctuations in a time-dependent background in this expanding Robertson-Walker space is given by this expression. And I leave this as an exercise to the student. We can define a canonically quantized mode function, right? So this thing is a mess, right? It's coming up with solutions to this is not obvious. But we can do a simple variable change that makes it into effectively a Klein-Gordon equation, turns it into a canonical variable by defining a new mode function v, which is just the scale factor times the field fluctuation. And if we do that, this equation of motion for delta phi turns into an effective Klein-Gordon equation, except it has an extra term, which is a time-dependent mass term. So the basic physics here is that field fluctuations in a time-dependent background are governed by a Klein-Gordon equation and the time dependence of the background is reflected in the presence of a time-dependent mass term in the Klein-Gordon equation. So let's look at the qualitative behavior of this Klein-Gordon equation, right? So I have a standard Klein-Gordon equation with this time-dependent mass term in it. Now I can take this thing and look at two boundaries, one in which is dominated by k-squared, which is the short wavelength limit, right? When k is big, when k dominates over the time-dependent term, right? So when the mode is much smaller than the horizon size, we don't care about cosmology, right? That's why the LHC works, is because we don't have to care about the Hubble parameter when we're calculating Feynman diagrams for particle wavelengths that are a femtometer, or much smaller, of course, in the LHC. Then we get essentially a Minkowski space Klein-Gordon equation, and we know what the solution to that is. It's just plus or minus IKT. Notice that this is still in terms of conformal time, right? So weirdly, what we get is we get a Klein-Gordon equation in terms of conformal time, But once again, at very short wavelengths, if we're talking about time scales very much less than the expansion age of the universe, conformal time and coordinate time become interchangeable with each other, right? As long as the change in the expansion rate of the universe over the time of our interaction in the LHC doesn't matter, we can swap conformal and coordinate time out. So this is the short wavelength behavior. So on short wavelengths, what we get, as we ought to, is bog standard scalar quantum field theory in Minkowski space. That's this limit. Now we look at the opposite limit. This is the long wavelength limit when the mode has been stretched to much, much larger than the horizon size. We get something that's very different. We get this weird equation where A double prime V is equal to AV double prime, which has a trivial solution that V is proportional to A. Right, so we no longer even have oscillatory solutions. We have this linearly growing solution in our Klein-Gordon mode function. But that's only in the mode function. In fact, the physical degree of freedom is delta phi. So in this super horizon limit, where we're very, very long in the asymptotic long wavelength limit, what we find is that this mode undergoes what's called mode freezing, that delta k goes to V over A, goes to a constant. So this can be seen schematically here. So in this region over here is smaller than the horizon size. This region over here is larger than the horizon size. This vertical line is the horizon. So this is the wavelength of the mode in units of the co-moving horizon size, plotted by the scalar field fluctuation amplitude, plotted as a function of the wavelength of the mode in units of the horizon size. What we see is oscillatory behavior on short wavelengths when we're in the Minkowski limit. And then what we see on long wavelengths is the new behavior that comes about because of the time-dependent background, which is this mode asymptotes out to a constant. This is this famous process of mode freezing, and this constant is non-zero. And what you're seeing here is that this is a momentum space representation of this Hawking radiation. That this thing, as it gets stretched out, this mode that is so we put the mode in a vacuum state at short wavelengths. When it stretches out to long wavelengths, in fact, it doesn't damp away, but actually goes to a constant, freezes into the background and sources perturbations. This is the holy grail. This is the thing that we want to calculate, is we want to calculate the amplitude of this thing in the asymptotic limit when it is well outside the horizon. Well, let's look at how we do this. So now we have to include actual cosmological expansion. So let's take the simplest this is an exactly solvable case. Let's take a constant equation of state. So let's let epsilon be some constant value. In the de Sitter limit, it's equal to -1, right? So that's the point, the limit of a cosmological constant, epsilon is equal to -1. As long as it's less than -1/3, we'll have accelerating expansion. And the simple solution to the Friedmann equation in flat space is that the scale factor just goes as the conformal time to 1 over epsilon. And then we can write the mode equation, has a very simple form, that this time-dependent mass term is given in terms of the co-moving horizon size and the equation of state. And this thing over here is now just a constant. So we know A of tau, we can calculate this AH. This thing is a constant. We can plug all of the dynamics for that into this thing. And what you find is that the solution to this thing is sum of Bessel functions in minus k tau. And so we can in fact write this, it's conventional to write this in terms of Hankel functions multiplied by the square root term. So now we have an exact solution to this mode equation that's valid at all wavelengths, short wavelength and long wavelength. And we can think about the short wavelength and the long wavelength limits as limiting cases of these Hankel functions in conformal time. And the order of the Hankel function is given by the equation of state. So in particular, when epsilon is equal to 0, this is a 3/2 Hankel function. It's a particularly simple case. And when epsilon is a little bit different than 0, then that index of the Hankel function differs. And this is where, for example, we're going to calculate the spectral index of density perturbations, and all that stuff depends on this Hankel function index in the solution to the scalar mode equation. So we have this solution. So that as long as the equation of state is constant or approximately constant, and we'll talk about the approximately constant case, which is the slow roll approximation after we do the simpler case of exactly constant. And then we can then have an exact solution to this equation of motion, which it turns out is a bunch of Bessel functions. Nothing terribly complicated. Here's the complicated part. Now we want to calculate the amplitude of this thing, right? So we know the behavior of this in time. We know the time dependence of this mode function, but we don't know the amplitude of it. The amplitude is set by a boundary condition at short wavelength by quantization. So in order to calculate the amplitude of this, we need to quantize the field, and we're going to canonically quantize our scalar field fluctuations in this time-dependent background as follows. So what we do is we Fourier expand our scalar field fluctuations delta phi, and we replace those Fourier coefficients as we usually do in quantum field theory. V of k is not the Mukhanov-Sasaki variable. The Mukhanov-Sasaki variable is the curvature perturbation, and I will define the Mukhanov-Sasaki variable later, okay? It's related to the Mukhanov-Sasaki variable, but this is actually just this is a free field fluctuation in the background. I'm not coupling it to the curvature. If I couple it to the curvature, I get the Mukhanov-Sasaki variable. I'll talk about that coming up, okay? So stay tuned. So this thing is, now we promote the Fourier amplitudes to operators and assume a canonical commutation relation for those operators, as one does. And then we can define a canonical momentum, which this differs from a Minkowski space canonical momentum in that if I take the Lagrangian is depends on the field and the field kinetic term, and so I can define the canonical momentum as the usual derivative with respect to of the Lagrangian with respect to the field kinetic term. That turns out in a time-dependent background to have a factor of the scale factor out in front of it relative to its Minkowski space cousin, right? So this is where this is where the expansion comes into the quantization condition, is that the canonical momentum actually has a time-dependent factor in front of it due to the cosmological expansion relative to what's familiar probably from Minkowski space field theory. And then I can write the canonical commutation relation between the field and the canonical momentum. And it is a straightforward proof to show that this results in a Wronskian condition on the mode function v sub k as follows, right? So this ends up, if you plug this canonical momentum into, so all the Fourier expansions apply the canonical commutation relations for the creation and annihilation operators, cancel out all the exponentials and the integrals, and the result is that you get a Wronskian condition on the k-space mode function, right? So this is the canonical momentum and field in position space. If you do all the Fourier integrals, and it's a straightforward exercise in standard scalar quantum field theory, you end up with a Wronskian condition on the mode function, where the time derivatives now, the relevant time derivatives, are with respect to conformal time, not coordinate time. That's the other difference here, is that in fact, the natural definition for the field theory is in units of conformal time, because that's where the metric is conformally Minkowski, and you can consistently define a quantum field theory and the conformally Minkowski metric in this way, all right? So now let's look at the limits of this thing, the limits of these Bessel functions, right? So what we have here is we know the form of the solution, right, which is these Bessel functions. Whoops. And now what we want to do, and we also have now a canonical commutation relation, which is a Wronskian condition on these Bessel functions. We can apply that canonical commutation relation to these Bessel functions, and we can normalize our field fluctuations. Here's how we do this. Let's take it in the short wavelength limit. And the short wavelength limit then is when the argument of these Bessel functions minus k tau goes to infinity, right? When this thing becomes large, it's short wavelengths. And we know that in the short wavelength limit, we recover a standard Klein-Gordon equation. So we have and using Feynman's rule, the same set of equations has the same set of solutions, because we know we have a Klein-Gordon equation at short wavelength. We know what the solution of this is. And so now we have these arbitrary normalization constants that we need to get rid of, right? So now we do two things. The first is quantization fixes one of these normalization constants in the following way. If we take this Wronskian condition on my mode function at short wavelength, we can derive the fact that that Wronskian condition is equivalent to that a squared minus b squared is equal to 1 for each independent wave mode k. In fact, we don't even need to take the short wavelength limit. We could apply this Wronskian directly to the Bessel functions, use Bessel function identities, and you get the same result. So this, in fact, does not depend on the short wavelength limit in any way, although it's easier to do in the short wavelength limit, and that's typically the way it's done in textbooks. It's a nice exercise to go through applying this Wronskian to the exact Bessel function field solution and derive this. And I'll leave that for students to do as well. So kind of a little bit of messy algebra and some Bessel function identities. So now what we have is we have one boundary condition, which is just quantization, which fixes the relative amplitudes of these coefficients A and B. And the second one is we select a vacuum state. This is another arbitrary thing that we assume. What we're going to assume is that at short wavelengths, this thing acts like a usual Minkowski space vacuum wave function from the point of view of a co-moving observer. So basically what we're doing is we're saying the vacuum we're defining, what we mean by a vacuum state in our quantum field theory, is the vacuum as seen by an observer that's co-moving with expansion. And this is called the Bunch-Davies vacuum, and it corresponds to a choice A is equal to 1, B is equal to 0. So that makes this Wronskian condition trivial, and this fully normalizes my wave function now, right? I have two conditions on these two constants. I end up to a complex phase, which is physically irrelevant. I end up with a normalized mode function that looks exactly like that at short wavelengths, right? I could, in principle, choose a different choice of vacuum, right? In general relativity, what you mean by in quantum field theory in a curved background, what you mean by the vacuum is observer dependent. This is where things like Hawking radiation and the Unruh effect come from, really, right? So a better way of understanding Hawking radiation is that the vacuum is observer dependent. And so an observer near the horizon of a black hole, an observer at asymptotic infinity, disagree with what you mean by a vacuum state. And the magnitude of their disagreement is a quantitative expression of the amplitude of the Hawking radiation. We're doing the same thing here. We're saying that the vacuum state, we're going to define it to be the vacuum state as seen by an asymptotic observer at short wavelength. And we're going to find that an asymptotic observer at long wavelength no longer sees a vacuum state, but sees particle excitations. This is the essence of Hawking radiation, and this is the calculation that we're doing here. So we take the vacuum to be the vacuum as seen by a co-moving observer at in the short wavelength limit. And then that allows us to fully normalize our wave function. And then all we do is follow that out to the asymptotic long wavelength limit and look at how big it is. See what, now that the mode is normalized, we can calculate its amplitude outside the horizon. And that gives us that delta phi term that we need to plug into the delta n formula to calculate the curvature perturbation. So, and the simplest example is de Sitter space. When epsilon is equal to 0 and I have exactly exponential expansion, right? P is equal to minus rho, I have a cosmological constant. The order of this Hankel function is 3/2. And so in fact, I have an exact solution that the Hankel function looks like this. And I have already assumed the Bunch-Davies vacuum, that I have only taken the e to the minus ik tau solution to this thing, right? So it turns out that a 3/2 Hankel function is an e to the minus ik tau multiplied by this term. If I apply canonical quantization to this, it's straightforward to show that the fully normalized wave function looks exactly like that. So this is just a short wavelength mode function multiplied by long wavelength modifications that are a result of the time dependence of the background, right? So this is a non-Minkowski solution, but it asymptotes to a Minkowski solution at short wavelength. Very neat, very clean. So now let's take this mode function, fully normalized, completely specified, and stretch it out to long wavelength. So here's my mode function. Now, if I take the long wavelength limit of this thing, what I find is that these terms go away, right? And this term goes to a constant. So the only thing left is that I over k tau term. So in the long wavelength limit, this mode function goes like that and goes in the long wavelength limit to just the inverse of the wave number in units of the co-moving horizon size, all right, or the wavelength in units of the co-moving horizon size. And then I can use this to calculate the wave function, right? So this is obviously time dependent, right? Because it has a factor of AH in it. But remember that the field fluctuation is the mode function divided by the scale factor. And that, since H is a constant, that goes to a constant as well. And I see exactly this phenomenon of mode freezing. And not only that, but I can calculate exactly the amplitude of that frozen mode by starting with the short wavelength mode, with the exact mode function that was normalized to a Bunch-Davies vacuum at short wavelength. I end up with now this famous result that the field fluctuation amplitude is proportional to the Hubble parameter, right? So at the end of the day, all of this quantum field theory and curved spacetime gives me this lovely, elegant result that I end up with a frozen field fluctuation whose amplitude is equal to the Hubble parameter. And I can write this now in more conventional form by the power spectrum. So another exercise left for the student is to show that if I take these my spatial field fluctuations that I expand out as Fourier integrals, if I do those Fourier integrals and take the vacuum expectation, the 2-point autocorrelation function of this thing, I can show that that ends up being a Fourier integral over the VK over A squared. So I end up with the following Fourier integral for the 2-point correlation function of the field. And I define my power spectrum as the power in the 2-point correlation function over a logarithmic interval in K. This is just a definition of what I mean by the power spectrum. It's a power per logarithmic interval in the autocorrelation function of the field at constant spatial points, right? So I take this delta phi squared evaluated x prime is equal to x, right? So this integral goes away. And then I have a power spectrum, which then ends up being defined as k cubed over 2 pi squared times this thing. But I already calculated this in the last slide. That's just my vacuum fluctuation function. So I end up at the end of the day with this very famous result that the power spectrum in free field fluctuations in an inflationary background is just given by h over 2 pi squared, right? So this is my famous result for free field fluctuations. Notice, so back to the question of, is this the Mukhanov-Sasaki variable? The answer is no. It's only the Mukhanov-Sasaki variable if you go into the de Sitter limit, and then this becomes difficult, and we're going to spend a lot of time talking about that limit, okay? So this is just any free scalar field in a de Sitter background. So I'm going to leave it to you guys to work out the more general case, so that now for some epsilon is equal to a constant, but not 0, the non-de Sitter case, which we're really interested in inflation, you can show that the Bunch-Davies condition corresponds to the positive Hankel function, right? So if I take the short wavelength limit of this general thing and then look at the e to the minus ik tau term, then I find that that corresponds to assuming only the positive Hankel function, and quantization fixes the normalization in this way, right? So all of this can be done analytically. It's just a couple of integrals and a few Bessel function identities. And then we can take the long wavelength limit of this Hankel function, and you can use Bessel function identities to show that in the long wavelength limit, that when minus k tau goes to 0, you end up with this asymptotic form for the power spectrum, right? All of this is just a straightforward plug and chug calculation from this point, but it's lengthy, and there's no particular reason to go through the details of it in lecture here. So now, here's the point, is that in the limit when epsilon goes to 0, I have this factor of h of 2 pi out there. So this still even applies in the limit when epsilon is non-zero. But then I have this little bit of k dependence on the outside. And in fact, this k dependence is determined. The k dependence of this function at asymptotic infinity is determined by the order of the Bessel function. And this is why it's this 3 halves minus nu that determines the k dependence of the ultimate resulting curvature perturbations, which is what we want to, which is an input to LCDM cosmology, right? So if we want to know the relevant parameter for LCDM, the slope of the power spectrum, we just need to know the order of this Bessel function, which is given by the equation of state during inflation. This is remarkable, right? So we can say, I have this input that I want to put into, say, my CMB fast or my CAM code, which is the slope of the power spectrum. Then all I need to know is what was the equation of state during inflation when that mode exited the horizon. There was a question about calculating delta phi is equal to 0. Can you put that question back up again, and I'll answer it? I missed it when it popped up in the chat. As soon as I see it again, I'll answer it. Okay. So this is the name of the game. Sorry. This would be a good time for a quick question about what I've just covered, because now I'm going to move to the curvature perturbation. Okay.
Okay, there is a raised hand.
Yes.
Aman, Gopi, can you unmute Aman, please? Aman Pawar.
Hello, Aman.
Can you
Gopi,
go
are you
to
there?
previous slides? The previous 2 slides.
That 2
I
slides.
need for short wavelength mode. Yeah, this one.
Yes, sir.
Here, previous one.
Did you ask from AV team help?
Okay.
Yeah, this one. Here, this Hubble parameter is time dependent, right? It is decreasing function of time.
No, it's not. This is de Sitter space. The Hubble parameter is constant. This is the de Sitter case.
Okay. Okay, thank you.
Yeah. All right. Anything else real quick?
Are there any other questions?
Okay.
I can't
see
see
2
any
raised hands.
now. Yeah.
Okay.
There are 2
Okay.
raised hands now. Aman has asked, Gopi, can you unmute Karthik, please? Karthik Raji. Yeah. Karthik, go ahead. Just a minute.
Yeah. Hi.
Go ahead,
My question is, if we were to, if we were to calculate the expectation value of delta phi, wouldn't we get 0?
No. That's
Right.
the point, is that you don't get 0 because you're in a curved background. That's the whole point, is that
No,
the
he's
expectation
asking
value
about
of phi you would expect to be 0 in a Minkowski space, but it isn't. Right. And so what we're calculating is the expectation value of delta phi squared. That's not 0. It freezes out. That's the essence of the calculation. All right. Did that answer your question?
Answer your question, Karthik?
I guess so.
Muted.
Okay.
Okay, maybe we can have these questions 30 minutes later in the question and answer session.
Yeah.
Yeah.
So we have a
sorry,
Q&A session today.
May I just?
Yes.
Okay. Yeah, can I ask the follow-up?
Sure.
Yeah, so what I was asking is, if I take the expectation value of delta phi written as, let's say, the field expansion that you have written down, sorry. So I seem to think that this the creation operator hits the vacuum, or the annihilation operator.
But we're not calculating the
hits
expectation value of delta phi. We're not calculating that. We're calculating the expectation value of delta phi squared. We're calculating the 2-point function, not the 1-point function. The 2-point function, the 1-point function vanishes. The 2-point function does not.
Okay, so the definition of delta phi is that it is the root
The square root of the 2-point function.
Okay, thank you.
Yes. All right. So now we know we can calculate the curvature, the perturbation in the free field fluctuation. That is the curvature perturbation on these flat hypersurfaces, right? So if we take the flat hypersurface, we can calculate the field fluctuation is effectively a free field fluctuation, and delta phi is just equal to the square root of the 2-point correlation function, which is non-zero, and that's just given by h over 2 pi. And then we know that dn by d phi, we can just write that in units of the field evolution rate in units of the Hubble parameter, right? So it's dn dt. So we can rewrite this in field variables as dn by d phi is just the expansion rate divided by the field velocity, right? That tells you the variation in n with variation in the field. And then we can write the co-moving curvature perturbation, the zeta. Now this really is the curvature perturbation, by promoting this flat space field fluctuation to co-moving hypersurfaces using dn d phi. And what we find is that this is equal to h squared over 2 pi phi dot, right? And this is the standard expression for the curvature perturbation that you're probably familiar with. An interesting thing is that this is equal to the ratio of the quantum fluctuation amplitude divided by the amount of field evolution in the Hubble time. So this is a really beautiful result, that the curvature perturbation power spectrum. So this is the bottom line from the quantum field theory. And in order to calculate observables and stuff, you don't have to even understand the quantum field theory. You just have to know this, is that the curvature perturbation amplitude is equal to the quantum fluctuation amplitude divided by the classical field evolution in a Hubble time. And that's equal to h squared over 2 pi phi dot, or in terms of the equation of state parameter, now we can use the Hamilton-Jacobi equation to write phi dot in terms of epsilon, goes as h over the square root of epsilon times a bunch of normalization constants. Notice that this should bug you. This is a standard result, right? Those of you who read papers on inflation have seen this a bazillion times. But this should really bug you, right? Because what happens, the de Sitter limit is when phi dot goes to 0. So I've just told you that I can do linear perturbations about an effect, do things that are perturbatively close to de Sitter space. I can calculate this perturbation, I can calculate this, the curvature perturbation amplitude in this linear perturbation theory. But then as my linear perturbation theory gets better and better and better, as I get closer to the de Sitter limit, my curvature perturbation amplitude diverges as my approximation gets better. So one thing I think that everybody who studies inflation wonders about is, what the hell? I mean, when phi dot goes to 0, this thing goes to infinity. What does that mean? We will answer that question tomorrow. So keep that in mind. We'll actually come up with a way to understand what this bizarre result means, because it's not very often you get something as your approximation gets better and better and better, your observable diverges, right? That makes no sense at all. And we have to unwind why it is that this thing goes to infinity when phi dot goes to 0, because our approximation should be getting better and not worse. Okay. But I'm not going to answer that question right now. So notice now that I have a free field fluctuation amplitude. Any free scalar field in this background, I can just calculate its fluctuation amplitude as h over 2 pi. And I can convert, if that field happens to be the inflaton, I can convert that free field fluctuation amplitude into a curvature perturbation using the delta n formula, and then I just end up with another factor of h over phi dot. That gives me the curvature perturbation. So now if I'm talking about tensor modes, gravitational wave fluctuations, it's straightforward to show that tensor perturbations in a Robertson-Walker background actually are free field fluctuations. They do not couple it to first order to the curvature. And so once I've done the free field calculations for gravitational wave modes, I'm done. The curvature, the tensor modes, there's a normalization factor here, but it's just given by h over 2 pi. So the power spectrum in gravitational waves is h squared over pi squared times m Planck squared. And then I can define the tensor fraction, right? So the tensor perturbation divided by the curvature perturbation using that delta n formula is then just equal to 16 times the equation of state parameter. This is the classic result for the tensor scalar ratio, is that this tensor perturbations are a free scalar field, curvature perturbations are not, and the ratio between those two things is just determined by this equation of state parameter, which does go to 0 in the limit of de Sitter evolution. And in particular, I also know from the asymptotic k dependence, if I'm near the de Sitter solution but not exactly at it, I have a certain k dependence in that asymptotic Bessel function. Yes, Sriram.
Well, this is Sriram. We are 10 minutes past the time, and we are meeting again for questions in 20 minutes.
Oh, holy cow. All right. My apologies. I lost track of time. So I will stop here with the consistency relation for scalar and tensor perturbations, and we will take up next time with the Mukana variable calculation.
So all the questions that are, I noticed there are a few questions. We will, no problem. We will
hit those questions in the Q&A. Okay,
yes,
so
absolutely.
the Q&A starts in 20 minutes? Okay.
In 20 minutes.
Cheers, guys.
18:10 local time, 18:30 we meet for the Q&A.
Okay, so that would be 8 o'clock my time, right? I will see you in 20.
Yes, 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 thank you.